Hello, everyone, and welcome to a presentation about our capstone project that we worked on together with Professor Yoon-Jin here at UCI. My name is Michael Jinko, and I'm here today with my team members Chen Si-yin and Connie Cheng. This is a quick look at the table of contents that we're going to cover. Let's start with the introduction. Our project is titled as Autonomous Driving Sensors at Extreme Environmental Conditions. First, let's look at what are the current needs in the sensors industry. As we all know, self-driving vehicles that move without the intervention of human driver play a key role in the vehicle industry. To realize autonomous driving, it is essential to extract imaging data from various sensors that are installed on the vehicle. In other words, it is important to better understand sensor performance in extreme environmental conditions. In this project, we focus on the camera sensor and three different environmental conditions: temperature, humidity, and sandstorm or dust storm. Now let's move on to our project goals and objectives. We had to develop lab equipment to experimentally evaluate sensors, optical cameras in our case, at environments and to provide guidelines for engineering solutions, simulate and accelerate environmental conditions, especially when driving, demonstrate collective data sets to conceptualize prognostics and health management for intelligent autonomous vehicles, and discuss the potential hardware or software solutions to mitigate environmental conditions and to improve the reliability and confidence of vehicle systems. Here is a quick look at our Gantt chart that we followed throughout the project's duration. This is a quick overview of the project flowchart. Inside the environmental box, the camera sensor was introduced to different environments. First is temperature that can put the lens under thermal stress. The second is humidity that can cause water droplet formation on the lens. And lastly, there is sand that can cause scratches on the lens. The damages are introduced to the camera, and then the data in form of images is collected from the defected cameras. These images are then restored and classified using our software. Now it's time to move on to the next part, which is the hardware design of our environmental box. On the right, you can see an illustration of how we imagine the box to look like in the beginning of the project. The goals of the design and manufacturing of the box were to create a sterile environment for camera stress testing, allow modularity for environmental inputs, and make it easy to use and durable for future iterations. First, environmental module is a humidifier that supplies humidity into the box. The goals for these modules were to closely approximate humidity conditions found in real driving conditions and be able to supply enough humidity such that air saturation is made possible and condensation can occur. The goals for the feeder system that is supplying the grain media into the box are as following. The media must accurately simulate environment that vehicles would find in real-world conditions. The feeder must have a repeatable mechanism to control the flow of the grain media, and the setup must be sturdy and not fail due to vibrations. Here is a quick look at our Pew matrix that we used to decide on our final feeder system design. As you can see, we considered 5 different design options, but ended up going with butterfly valve and vibration module. The blower system used to blow sand and hot air onto the camera had to accurately simulate environment that vehicles would find in real-world conditions, which in the US is on average between 6 to 12 miles per hour. It must have a repeatable mechanism to control the airflow, and it must not fail due to vibrations. Here is again a quick look at Pew matrix that we used to select our final heating module design for our box. From the picture, you can see that we ended up using an inline heater to heat up our airflow and raise temperature within the box. I will now pass it to Chen, who will tell you more about the manufacturing of our setup and test results that we achieved.
All right, let's have a quick overview for our experimental setups. Let's start with the environmental box itself. The box we picked is a locally sourced box. It's weatherproof, IP66 waterproof. It's designed for electronics housing and wired connections in an extreme weather condition. So it has a shorter lead time compared to the manufacturing box with aluminum. And so it has also has a minimal impact to schedule and overall functionalities. And it's increased the build quantity. Let's step to the feeder system. The feeder system center was marked 6.5-inch inches to the left of the box, and the team is trying to keep the feeder system closer to the camera to increase the chance of scratching. The team used the 2-inch MPT drill through the box, and the feeder system was secured in position with the 2-inch MPT adapter due to the diameter difference. And 2-inch MPT valve was flipped because there's not enough space to turn the handles clockwise.